In this presentation, I'll be explaining three-phase half control bridge. Three-phase half control bridge with RLE load or three-phase semi-converter it is called. Three-phase semi-converter. Now, this is the circuit topology of a three-phase semi-converter, in which it is only one half is being controlled, because that is why only in each leg one device is the SCR controlling switch, other one is a uncontrolled switch diode is coming. Therefore, T1 is number like T1, T2, T3. These are the SCR at the top. Here diodes are there, which is course number D1, D2, D3 like this number, and this is the RLE load here, and this is the input three-phase supply is given here. Now here the SCR which can be triggered or that can be this should be forward bias. Therefore, which is more maximum positive, that device can be forward bias out of T1, T2, T3, which is maximum bias can be fired or can be triggered. And negative side means that there's no control of that one, which is the maximum negative, negative voltage that will be conducting. Therefore, here if you see that one, during this one, if negative device means that during this period, which device is maximum. For example, in this one, here the device that is connecting the phase A will be maximum negative, and this is the maximum negative with the negative with the phase C, like that one. For which that corresponding diode will be conducting that one, and based on that one, the switching devices that are conducting different durations are marked like this one. For alpha equal to 30. Therefore, this is the phase voltages VA, VB, VC. As I already explained here, alpha is measured from this crossing point for phase A, from this one for phase B, and from this one for phase C. This we are considering for alpha equal to 30. Therefore, firing angle is only for this upper or this SCR T1, T2, T3. In that one, here the firing angle is taken as 30. That is why here this is T1 is triggered here. T1 is triggered, that device is conducting for 120-degree duration. Again here T2, that is second phase B, that's connected, that is triggered. Again 120, that is T3 is fired. Like that it goes from the upper side. And the lower side diodes mean which is having the maximum negative that will be conducting. For example, here this is conducting means that here the diode, D1 will be conducting. Diode D1 will be conducting because that is the maximum negative here. That is why that D1 will be conducting. Therefore, the maximum negative is that phase that diode will be conducting. Therefore, that is the way in which that devices that are conducting on the negative side or this diode side is marked as here D1, of course D1, D2, D3 like it is marked. Therefore, at any instant we can see that one from the SCRs, the top one from the SCR and one from the diode will be conducting. Which diode and diode pairs are conducting at different instant, that will be varying that one. Based on that one, you will be getting the line voltage. For example, in this case, for here, if you see that one, when T1 is triggered here T1 is triggered. When T1 is triggered, T1 and D1 are conducting. T1 and D1 are conducting means that here T1 is conducting and here D1 is conducting. For phase A and phase C, here phase C comes, here phase A comes. Therefore, the voltage here equal to VAC. That is why we will be getting it is here we can say that one. In that one, no, here phase T1 and here D3 is conducting, or T1 and D3 are conducting, not D1. T1 and D3 are conducting. D3 means here, D3 means VP. Here B phase is coming, here A phase is coming. Therefore, here A and B, VAB comes, here VAB comes. Therefore, based on the device on the positive side and this diodes, the corresponding phases will be connected to here, that line voltage will be getting. Therefore, that this is the shape of the voltage that is coming across the RLE load based on the devices that are conducting on the positive side and on the negative side. Therefore, that is the diode will be forward bias when its cathode is most negative. Therefore, D1 is forward bias from 90 to 220. From 90 to 220, it is, for example, here D1 is forward bias, or that is forward. And D2 will be forward bias from 210 to 330. And D3 will be forward bias from 330 to 90 to 210 and 210 to 330, and from 330 to 4, of course, again 120, that is, it is equal to 450. It is each diode will be conducting for, 150, sorry, 120 degrees. For based on that one, you can find out what are the devices They are connecting in each instant. As I explained in the previous slide here, this is the, the topology of the circuit. Here, this is the thyristors and this is the diodes. And based on that different instant, as I alpha to 30, different, for example, here we can get T3 and T3 and D3. When T3 and D3 are conducting, corresponding voltage here will be VCB. And similarly, next we will be conducting here T1 is triggered, or T1 is the incoming SCR, and of course T3 is the outgoing SCR. Therefore, T1 and D3 are conducting. T1 and D3 means here the phase A, and of course D3 means phase B. Therefore, he'll be getting VAB. Like that, which looking from this one, you can write which is from the positive group and which is from this negative diode is conducting. Based on that one, you will be getting corresponding voltage across the RLE load. That is indicated in the table. Different instance, what are the devices that are conducting? One from this upper one, thyristors, and one from the lower diode one. Based on that one, you'll be getting the voltage across the RLE load. Therefore, the freewheeling mode of operation of bridge connected rectifier can be realized by replacing half of the thyristor with the diode. Therefore, when when this is corresponding to alpha equal to 30. Now let us see different firing angles in the next slide. Now, if the firing angle now increase from 30 to say 90 here, that devices will be the device which are conducting will be different. That will be shifted here. This will not be changing. D1, D2, D3, that position is not changing. But T1, T2, that is changing now here. T1 is shifted by again. That because 90 degrees, the first 90 plus 30 comes. Therefore, alpha become 120. Start from 120 here. For 120, again plus 120, again plus 120 that comes. Therefore, the devices that are conducting, that will be looking from the diagram itself. It's very clear that, for example, 0 to 90, if you calculate the 0 to 90 here, 0 to say 90 here, T3 and D3, when both T3 and D3 are conducting, say T3 and D3 are conducting, you can be getting what is the voltage VCB will be getting. T3, that is this voltage will be positive and it will be negative. VCB will be getting. But the same thing from 90 to 120 duration, that is from 90 to 120 duration, we can see that T3 and D1 are conducting. When T3 and D1 are conducting, that is here, T3 and D1 are conducting, these are shorting that one, you will be getting 0 voltage here. That is why you will be getting a 0 voltage, because alpha equal to 90 here, 0 voltage is getting. That again you can see for different, then T1 and when T1 and D1 are conducting. When T1 and D1 are conducting, A phase is available here and here C phase is available. We will be getting VAC, will be getting. Therefore, there are certain duration for which both control switch as well as uncontrolled switch both are conducting. During that period, you will be getting 0 output voltage across the RLE load. That is marked here. During these periods, you will be getting 0 voltage. That is marked in the table here. T3 D1 0 voltage, like T1 D2 0 voltage, and T2 D3 0 voltage. Because in that case, these are getting shorted, and you will be getting 0 voltage across the RLE load. And if you see the corresponding current in through the phase as the source current here, you can see that one only when this is conducting, you will be getting a positive current. And here, for example, this one and this one is conducting. T1 and of course the D1 are conducting. Here current will be like this one, you'll be getting a positive current. But when both these are conducting, when these two legs are conducting, you'll be getting 0 current. And again, when this is conducting, when this diode is conducting, you'll be getting a, because the lower one is conducting, you will be getting a, of course, a negative current here. Therefore, this is the shape of the current that is at the input of this line, source current in the phase A. This is the shape of the current. And what we are assuming that the load current is a constant, continuous current, constant current I naught is getting. And this is the shape of the current at the input side of the phase A. Other phase will be 120 degree shifted one. Therefore, this is the voltage across the load, and this is the line current in the phase A here for a firing angle of 90 degree. Now, these are the devices that are conducting for different duration from 0 degree to 360 degree. This I already have explained in the previous slide. Here, for a firing angle of alpha equal to 30 here, this is the shape of the current. This is the shape of the current. Previous slide, it was for 90 degree. For 30 degree, this is the shape of the current. Plus I naught, then 0 duration. When none of that current, and again it is equal to minus I naught. Again, this is the shape of the current that is flowing, or the line current. And of course, the load current, we are assuming that constant load current, because we have continuous conduction, we are assuming that load current is continuous and it's ripple free. In that case, the source current will become like this. Load current is a constant, but source current is having a harmonics. A lot of harmonics are there. For this is for corresponding alpha equal to. This is to show what are the devices that are conducting for different firing angle. When firing angle equal to 0, these are the devices. Because this will not be changing. The diode that will be, because this diode will be conducting which are the maximum negative phases, that is not changing. That is always all are same. You can see that one, or D3, D3, D1, 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 D2, 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 like that, D3, D3, D3. That's not changing. What change in this one? The device that is on the positive group, that will be changing based upon the firing angle. If firing angle equal to 0, it is like this one, T1, T2, here again 120 degree, T3 again one, that's coming. But if there's a phase shift of 30 degree, that T1 now instead of here it is shifted to 30 degree here. But everything will get shifted. Again here 60 degree means again it is shifted to 30 degree. That is this one again shifted to total from here 60 degree, that is shifted. For the devices that now T1, T2, D2, D3, that is shifted, but this is not changing. At any instant you can see that one from the positive group, one from the negative group. If the devices in the same length they are conducting, then output voltage equal to 0. So these are different phasing firing angle, alpha equal to 0, alpha equal to 30, and alpha equal to 60, and the devices that are conducting. Now conducting the same thing here, again the firing angle equal to say 90 degree. You can see that D3, D1, D3, D1, D2, D3, that's not changing. But here it is shifted again. T1 is shifted now here. Alpha equal to 90 degree. For totally here it become now 120 comes here. From here if you calculate 30 plus 90, 120 comes from here. For T1, then again 120, after 120 T2, again after 120, like that. Now we can find out what are the devices at different instance they are conducting in watching this one. Similarly, when alpha equal to 120 degree, firing angle of this thyristor is 120 degree, again that is shifted. From here T1 is again, this for 90, 120 means again it is shifted to 30. Start from here, that is from here. For T1, again 120, after 1 T2, again after 120 T3, that comes. And other things are same, D1, D3, D1, D2, D3, like that one. Now you can find out what are the devices that are conducting. Based on the device you are conducting, you are getting the output voltage across the RLE load. One from the positive group, which are the thyristors, one from the negative will come, then you will be getting corresponding line voltage. If the devices from the same phase, same length they are conducting, of course you will be getting a 0 voltage. For example, if this thyristor and if the diode, are conducting, you will be getting a 0 voltage. But if you are conducting this thyristor and this diode, then you will be getting corresponding line voltage here. Therefore, the devices which are conducting decides the voltage average, the voltage that is available across the RLE load. As we have seen that if alpha is less than 60, the output voltage is continuous, and as we have seen here, the output voltage is continuous. We already seen here for 30 degree here. This is the output voltage, and if alpha is less than 60, output voltage is continuous, and if alpha is more than 60, we can say that there will be discontinuity in the. Of course, here you can see that output voltage is having a discontinuity. You can see that one. But here it is continuous. If alpha is less than 60, it's continuous. If alpha is more than 60, firing angle of this thyristor is more than 60, there will be a discontinuity during which the output voltage equal to, there are certain duration which the output voltage equal to 0. That is the case. Now there's an equation to find out what is the average output voltage across the RLE load. Of course, the DC voltage here, we have to alpha plus 30 to 90. Alpha plus 32 from 90, root 3 Vm sine omega, because we are taking a line voltage, that is why 30 degree shift is there, and the magnitude is also equal to root 3 line voltage is there, root 3 times Vm comes, because that's why root 3 comes, the line voltage, not the phase voltage. Root 3 Vm, a 30 degree shift is the d omega t. We are integrating that one from the limit alpha plus 30 to 90 degree. Then again from 90 to alpha plus 150, again 90 plus alpha, this duration, that's equal to root 3 Vm sine omega t minus, of course, the minus 30 degree, because that phase, we are based upon the which phase is conducting, we can say VAC, we will be getting sine omega t minus 30, that's why minus 30 comes there. And of course, this is like that one, there will be under 2 pi, there will be 3 pulses, like see 1, 2, 3. Therefore, these three pulse, this area, actually this area, that is we are multiplying with 3 and that is dividing over 2 pi. For 3, we are taking the total this area, that is integration, that 3 times will give the total area under 2, that is divided by 2 pi. Therefore, we will be getting the average voltage. Now, if you calculate that one, we will be getting 3 root 3 Vm by 2 pi alpha plus 30 to 90 sin omega t plus 90 d omega t plus integral 90 to 150 sin omega t minus d omega t, or we'll be getting 3 root 3 Vm by 2 pi into 1 plus cos alpha. Previously, it was 3 root 3 Vm by 2 pi cos alpha for a continuous conductor or the fully controlled 6 pulse converter, but for a semi converter, the equation now is 3 root 3 Vm by 2 pi into 1 plus cos alpha. This is for the case when alpha is less than or equal to 60 degree. So this is the average value of the voltage. Now let us see a problem in which a DC voltage 560 volt is required at the output that is across the load. You require 560 volt here, and the firing angle equal to 20 degree for this thyristor. Find out the RMS value of the input voltage. What should be the voltage to be applied here? Of course, RMS value of the input voltage. That's a question here. Then both cases, one we consider a three-phase fully controlled rectifier, that is all our thyristors T1, T3, T1, T3, T5, T2, T4, T6. It's a fully controlled rectifier. Second one, same here and topologies. These thyristors are replaced by diodes called semi-converter or 3-pulse converter, in which it is equal to 3-phase semi-converter in continuous conduction. Both are in continuous conduction mode. Okay. Now let us see first one. That is, in a 3-phase fully controlled rectifier, the average voltage that is across equal to 3 Vm by 3 root 3 Vm by pi cos alpha, or 3 VML by pi cos alpha, the line voltage, or it's the phase voltage, maximum value of phase voltage, it equal to 3 root 3 Vm by pi cos alpha. Vm is the maximum value of the phase voltage, root 3 Vm. Phase voltage, we have to find out actually this one, and alpha is given as 20 degree. 20 degree firing angle is 20 degree, and of course the DC requirement is 560. You substitute in that equation 560 equal to 3 root 3 Vm by pi into cos 20. That is here 560 is the VDC. Alpha 560 equal to 3 root 3 Vm by pi into cos 60. From this equation, the unknown is the maximum value of the phase voltage Vm. Vm you will be getting it equal to 360.3 volt. Maximum value of the phase voltage equal to this one, or its RMS value equal to that divided by root 2. Equal to 254.77 volt is the RMS value of the phase voltage. That is the it is required to firing out the RMS value of the input voltage. Of course, phase voltage is this one, and line voltage is equal to what we have calculated is this one. So this is the RMS value of the phase voltage in order to get a average output voltage of 560 volt for a firing angle of 20 degree. That's a in continuous conduction mode of fully controlled rectifier. In continuous conduction mode of in a semi converter, but we already discussed here. In that one, the equation average voltage equation equal to 3 Vm by pi, 3 root 3 Vm by pi, or 3 root 3 Vm by 2 pi actually. 3 root 3 Vm by 2 pi into 1 plus cos alpha. 3 root 3 Vm by 2 pi into 1 plus cos alpha. Same as previously here. The same voltage 560 equal to 3 root 3 Vm by 2 pi into 1 plus cos 20. And the unknown is here Vm. Then you will be getting it is equal to 349 volts. 349.1 volts is the it is the maximum value of the of course voltage, the maximum value of the phase voltage, and the RMS value of the input phase voltage equal to maximum value divided by root 2. It is equal to 246.85 volts. That is in a semi-converter, 3-phase semi-converter in continuous mode, the RMS value required to have a same DC voltage 560 volt is equal to 246.85 volts. And if it is a 3-phase fully controlled rectifier, it is equal to 254.77 volts.